Welcome back to the quantum mechanics series, guys. Today we're going to look at chapter 2. I think it's actually useful to read every single word inside each of these chapters because we learn the theory together. If you figure out there's a problem in your understanding of a problem, most of the time go back to the theory, check out some of these worked problems. There's examples in each of these sections. In the previous video we read this whole chapter. I think now, since we're on a pretty heavy chapter, this second chapter is very dense. We're going to go one section at a time per video. So today we're going to read about stationary states, try to do it as fast as possible. Then we're going to do infinite square well. Then the harmonic oscillator, which has two sections. We'll do the free particle as a separate video. The delta function potential, that also has two sections here. And then the sixth and last video, the finite square well. So let's start. Chapter 2, time-independent Schrödinger equation. Section 2.1, stationary states. In chapter 1, we talked a lot about the wave function and how you use it to calculate various quantities of interest. The time has come to stop procrastinating and confront what is logically the prior question. How do you get psi in the first place? We need to solve the Schrödinger equation, which is shown to us again here. For a specified potential V of x of t, x and t. In this chapter, and most of this book, I shall assume that V is independent of time. In that case, the Schrödinger equation can be solved by the method of separation of variables, the physicist's first line of attack on any partial differential equation. We look for solutions that are products. So we decompose psi, which is the main wave function inside the Schrödinger equation, and we split it up into two different. So we have a lowercase psi, which is only a variable of x, and we have this phi, which is a variable of t. And we take the product, and that gives us the full wave function. Where psi, lowercase, is a function of x alone, and phi, I'm going to just call this phi, is a function of t alone. On its face, this is an absurd restriction, and we cannot hope to obtain more than a tiny subset of all solutions in this way. But hang on, because the solutions we do get turn out to be of great interest. Moreover, as is typically the case with separation of variables, we will be able at the end to patch together the separable solutions in such a way as to construct the most general solution. For separable solutions we have, boom, so partial derivative of the full wave function psi with respect to t is now equal to this. So we just take a derivative of this full thing and we plug in our separation of variables. Since psi of x does not depend on time, it gets pulled out of the derivative, and the derivative applied to phi now becomes a full derivative because phi only depends on time. So the partial derivative turns into a full derivative. And then we find the second order derivative with respect to position. Same kind of thing, phi gets pulled out because it does not depend on position, and the lowercase psi, which only depends on position, now gets a full second order derivative. We're computing these things so we can plug them into the Schrödinger equation here and simplify it. Ordinary derivatives, I call them full, but this guy calls them ordinary. And the Schrödinger equation reads, boom, so we plug this in, IH bar, we have a psi here, which we plugged in from this. And then this thing here, we have a phi here, which comes from this. The V is the potential, and we also have psi and phi here. Why do we have that? Because we replaced this with the separation of variables product over here. Nice. So this is our modified Schrödinger equation, which we are setting up in order to solve it using separation of variables. Keep that in mind. Or dividing through by psi times phi, so we just divide both sides to cancel this thing out. We get V on its own. Get this AI assistant thing out here. We get V on its own. We get 1 over lowercase psi over here and 1 over phi over here. Now the left side is a function of t alone, and the right side is a function of x alone, number 2. So this is very important. Check out the left side. Everything here depends on time. We have a function that depends only on time, and the derivative with respect to time. Then the function here, I, h bar, are constants. On the other side, we have h bar squared, 2m, these are constants, 1 over psi. Psi is a function that depends on x alone, and we have the function again here, which depends on x alone. And here, Griffiths said that we're going to assume that the potential doesn't change in time, the potential only changes with respect to position. So we've separated the equation with x-dependent stuff on one side and t-dependent stuff on the other side. This is important, so let's check out this number 2, what it says here. Number 2 is here. Note that this would not be true if v were a function of t as well as x. Cool, thank you. Now the left side is a function of t alone and the right side is a function of x alone. The only way this can possibly be true is if both sides are in fact constant. Otherwise, by varying t, I could change the left side without touching the right side, and the two would no longer be equal. This is super, super smart. This thing here is very, very smart, and from this book I learned this, and I apply it to pretty much every problem of this brand, where one side of the equation depends on one variable, the other side depends on the other. The only way this can be true is if both sides are constant because of this one thing that he just said here. So if I want, I can turn the knob on the left side and keep the right side constant, right? Because the variables that those sides depend on are different. So I can just manipulate one without affecting the other. And if I do this, then this equality breaks. So the only way this equality can be true is if both sides are constants. Super, super smart kind of deducing kind of logic here. That's a subtle but crucial argument. So if it's new to you, be sure to pause and think it through. For reasons that will appear in a moment, we shall call the separation constant E. So since we just now determined that both of these are equal to the same constant, we call this side E, and we write that equation here, and we call this side also equal to E, which we use it over here. So this side gets manipulated to get this. You just move some variables around, and this side over here does not get manipulated. We just get, we just move it down. Actually, no, it does get manipulated. We multiply both sides of the equation by this lowercase psi. So we get psi on this side, psi on this side, and psi is gone over here. And this is the equation. This one is boxed. Also, keep in mind, this equation here only depends on time. So this one only depends on time, this one only depends on position. Separation of variables has turned a partial differential equation into two ordinary differential equations. This is super sick. I'm going to highlight this as well. The first one of these is easy to solve. Just multiply through by dt and integrate. So here we have dt, multiply both sides by dt. This is not really a mathematical trick. Mathematicians hate this, but physicists are okay with this. So you have a dt here, multiply both sides by dt. This dt gets canceled, the dt becomes over here. Then you integrate both sides. With this side you integrate with respect to phi, and this side you integrate with respect to dt. And then you get some exponential, I think. Let's see how he solves it. The general solution is c e to the power of minus I e t over h bar. But we might as well absorb the constant c into psi, since the quantity of interest is the product psi times phi. Then let's read 3. Using Euler's formula, this one here, you could equivalently write, okay, interesting. The real and imaginary parts oscillate sinusoidally. Mike Casper dubbed psi the wiggle factor. It's the characteristic time dependence in quantum mechanics. Nice. So since we broke apart the equation, the time-dependent Schrödinger equation, into two sets of variables, the time-dependent part and the x-dependent part, here we are solving just the time-dependent part, and we get this thing called the wiggle factor, which is named by Mike Casper. The second equation, 2.5, which is this one. So we solve the time-dependent version. Here is phi of t. It is an exponent related to the energy and the time, and it has an h bar and an I in there. Now we're going to move on to just the time-dependent equation, and this one is the important one. The second equation, 2.5, is called the time-independent Schrödinger equation. We can go no further with it until the potential V is specified. So this equation here, we were able to solve because everything inside is constants, or it is the function that we are trying to solve for. In this case, we solve the function. It's just a standard differential equation. If you don't know how to solve this, don't stress. Just search up online how to solve first-order differential equations like this, and you're going to get an exponential solution like this. The constants over here are also in the top here. Let's actually see how this works. So the first derivative with respect to time of some function equals that function itself times this jumble of mess over here. So if we take a derivative with respect to time of this function, the derivative of the exponential is just the same exponential itself, so we get this, but we also, by the chain rule, drop down this factor over here in the front, except the t, so that factor gets dropped down, minus IE, and then h bar, and then h bar. So you can solve this whatever way you want, don't stress about it too much. But this second equation here that we got from separation of variables, we cannot solve because v is unspecified. It is a function that depends on the system that you're exploring. The time part is general for all systems, but the position-related equation, it depends on your potential because the potential depends on the position. So we need a v of x to be specified. The rest of the chapter will be devoted to solving the time-independent Schrodinger equation for a variety of simple potentials. But before I get to that, you have every right to ask, what's so great about separation of separable solutions? After all, most solutions to the time-dependent Schrodinger equation do not take the form boom, which is a multiplication of these two functions, which we got from separation of variables. I offer three answers, two of them physical and one mathematical. Let's take a look at this. 1, 2, 3. And then we read one more page, one more thing, a problem, and then we're done the chapter, or we're done the section. So let's see why Griffiths likes separation of variables as a way to proceed with the Schrodinger equation. 1, they are stationary states. This is the section title, so it is pretty important and it's bolded. Although the wave function itself, psi of x of t, is equal to this position-dependent portion and this time-dependent wiggle factor, does obviously depend on t. Probability density, which is the square modulus, or absolute value squared, or psi star psi, if it's a complex thing, or it's written here. If psi is complex, psi star psi is how you get the absolute value squared of a complex thing. This equals psi star e to the plus, this is how you get a complex conjugate of something with an I, a function with an I in there. You turn this to a plus, times psi, right? So this is the psi star part, boom, all the way up to here with the h bar, that is the psi star. And then we have the psi part over here. This gives us psi of x squared. So it looks like the time-dependent portions here cancel out because we have an exponent to the positive something times an exponent to the negative something. These things cancel out and give you 1, so we just get the absolute value squared of the time-dependent thing. So these stationary states, or the probability density, does not care about this time portion. It only cares about the position-dependent wave function, psi, the lowercase psi. So it does not depend on, the time dependence cancels out. Number 4, let's read number 4 too. For normalizable solutions, E must be real. See problem 2.1. Okay, I don't know what that means yet. Don't stress about it, we're going to see it later. The same thing happens in calculating the expectation value of any dynamical variable. Equation 1.36, which we saw in the first chapter, reduces to this. And we have psi over here and psi over here. This is the lowercase psi, the psi that depends only on position. Every expectation value is constant in time. We might as well drop the factor phi t altogether and simply use psi in place of psi. Indeed, it is common to refer to psi as the wave function, but this is sloppy language that can be dangerous. And it is important to remember that the true wave function always carries out the time-dependent wiggle factor. In particular, expectation value of x is constant, and hence equation 1.33, I don't know which one that is, expectation value of p equals 0. Nothing ever happens in a stationary state. 2. There are states of definite total energy. In classical mechanics, the total energy, kinetic plus potential, is called the Hamiltonian. Here we have the Hamiltonian. It depends on position and momentum. It equals the momentum squared over 2m plus the potential, which is dependent on your system, and that is a function of x alone. The corresponding Hamiltonian operator obtained by the canonical substitution, p goes to negative I h bar, partial derivative with respect to x, is therefore, boom. So we've basically created a Hamiltonian operator in quantum mechanics by doing this canonical substitution. If that scares you, don't stress about it. Just look at how h from classical mechanics is similar to h of quantum mechanics. We have a p squared, which in quantum mechanics we saw P is equal to this. So you take all of that, square it. We have a 2m in the denominator, 2m in the denominator, and we have a v of x, v of x. Don't stress if this is confusing. Just keep in mind the similarities between quantum and classical here, and the Hamiltonian is important. Thus, the time-independent Schrodinger equation can be written as boom. So this is the time-independent Schrodinger equation. We have the Hamiltonian multiplied by psi, which is a function only of x, equals E. That's separation constant, which we were trying to figure out what it is, and it turns out to be energy. That's why he's using the letter E. If you don't know why it's energy, don't stress about it. We're going to see later. And then you multiply this as well. This also looks like an eigenvalue equation or eigenvalue problem. If that is confusing to you, again, don't stress. We're just reading. And the expectation value of the total energy is expectation value of H. Sandwich the operator H between psi star and psi. Integrate with respect to the variable psi depends on, which in this case is only x. Boom, integral over all space. We get E from this equation. Boom, the E comes out. Boom, you have the absolute value squared of the psi, and that gets converted to the full psi here. Not too sure why. But then this normalizes to 1, and then you get H. So the expectation value of, you get E. Expectation value of H, the Hamiltonian operator, is equal to E, the energy. Notice that the normalization of psi entails the normalization of little psi. Moreover, H Hamiltonian squared operator acting on little psi is equal to H then acting on psi, which is equal to E times psi, and you can pull the E outside because it's a constant. The operator acts on the psi only, and then you get E squared. So the operator here, well, I guess this line, summarizes what's on the previous line. Expectation value of the Hamiltonian operator squared is equal to the energy squared. Same kind of procedure as in this line here. Why are they telling us this? The variance is calculated. Variance of H is sigma squared subscript H is equal to expectation value of H squared minus expectation value squared of H is equal to E squared minus E squared, which equals 0. Remember, if sigma equals 0, then every member of the sample must share the same value. The distribution has 0 spread. Conclusion. A separable solution has the property that every measurement of the total energy is certain to return the value E. That's why I chose the letter for the separation constant. Not sure what all that meant. Let's just keep reading. The general solution is a linear combination of separable solutions. As we're about to discover, the time-independent Schrodinger equation, equation 2.5, yields an infinite collection of solutions, psi 1, psi 2, psi 3, and so on, which we write as psi subscript n, each with its associated separation constant, E1, E2, E3, all the way up to En. Thus, there is a different wave function for each allowed energy. Here we have psi 1, the full wave function, which depends on position and time. We have psi 1 of x multiplied by this time-dependent wiggle factor, and inside the exponent here we have E subscript 1, which relates to the first here wave function solution. Then we have the same thing, subscript 2, and the energy has subscript 2. Now, as you can easily check for yourself, the time-dependent Schrodinger equation, equation 2.1, has the property that any linear combination of solutions is itself a solution. Once we have found the separable solutions, then we can immediately construct a much more general solution of the form boom. So this is very important. The full wave function you can create as a like Fourier series of the different separable solutions with specific weights, Cn. We're going to look at this more deeply. Let's just keep reading. It so happens that every solution to the time-dependent Schrodinger equation can be written in this form. It is simply a matter of finding the right constants, C1, C2, and so on, so as to fit the initial conditions for the problem at hand. You'll see in the following sections how all this works out in practice, and in chapter 3 we'll put it on a more elegant language. But the main point is this. Once you've solved the time-independent Schrodinger equation, you're essentially done. Getting from there to the general solution of the time-dependent Schrodinger equation is in principle simple and straightforward. A lot has happened in the past 4 pages, so let me recapitulate from a somewhat different perspective. Here's the generic problem. You're given a time-independent potential v of x. Then the starting wave function and the starting wave function psi of x at t equals 0. Your job is to find the wave function psi of x at all time for any subsequent time t. To do this, you must solve the time-dependent Schrodinger equation, equation 2.1. The strategy is first to solve the time-independent Schrodinger equation, equation 2.5. This yields in general an infinite set of solutions, each with its own associated energy. To fit psi at t equals 0, you write down the general linear combination of these solutions. Boom. The miracle is that you can always match the specified initial state by appropriate choice of the constant Cn. To construct psi of x comma t, you simply tack onto each term its characteristic time dependence, its wiggle factor, which is this exponential thing. And then we have this equation here. Let's see what it looks like. Okay, interesting. Let's see these little points here. In principle, any normalizable function is fair game. It need not even be continuous. You might actually get a particle into that state is a different question. And one curiously we seldom have occasion to ask. If this is your first encounter with the method of separation of variables, you may be disappointed that the solution takes the form of an infinite series. Occasionally, it is possible to sum the series or to solve the time-dependent Schrodinger equation without resource to separation of variables. This is nicely illustrated. Okay, just looking at those little extra things there. The separable solutions themselves, psi subscript n is equal to the time-dependent psi subscript m, and the wiggle factor with the energy subscript n are stationary states in the sense that all probabilities and expectation values are independent of time. This is why you call them stationary states. They don't depend on time. But this property is emphatically not shared by the general solution, equation 2.17. Boom. Very sad. The energies are different, and for different stationary states, and the exponentials for different stationary states, the exponentials do not cancel when you construct psi squared. Okay, this is interesting. Example, we're going to read this example later, just get some of the theory. You might be wondering what the coefficients Cn represent physically. I'll tell you the answer, though the explanation will have to wait until chapter 3. Cn squared is the probability that a measurement of the energy would return the value En. A competent measurement will always yield one of the allowed values, hence the name Cn squared is the probability of getting the particular value E. Of course, the sum of these probabilities should be 1. Boom, normalization. And the expectation value of the energy must be this. We'll soon see how this works out in some concrete examples. Notice finally that because the constants Cn are independent of time, so too is the probability of getting a particular energy, and a fortiori, the expectation value of H. These are manifestations of energy conservation in quantum mechanics. Then we have a problem, another problem, and the infinite square well. So what did we learn here? A lot of things, but I'm not here trying to make this video very long. I'm here to just read the chapter. We're going to talk about the theory and what we learned in a future video. If you guys want to see something specific, let me know. Thank you as always for watching. I'll see you guys in the second section video.